Hello and most welcome to 1297 of the series. I will finish off the constructive mathematics with an extra addition, but firstly Stephen M Rosen's article Quantum Gravity will finally see its conclusion. And I left off last time at page 21. In the course of questioning contemporary efforts to arrive at a workable theory of quantum gravity, Lee Smolin made this confession: there is something basic we physicists are all missing, some wrong assumption we are all making. Smolin goes on to say, I strongly suspect that the key is time. Time is represented as if it were another dimension of space. Motion is frozen, and the whole history of constant motion and change is presented to us as something static and unchanging. Sorry. Sorry. We have to find a way to unfreeze time, to represent time without turning it into space. I venture to say that regrounding theoretical physics in phenomenological philosophy has the effect of unfreezing time. Merleau-Ponty's depth dimension is not simply a dimension of space, nor is it even a domain of space-time. In the Einsteinian sense, in which time is essentially spatialized. A better term for the life world dimension is time-space. This was Heidegger's name for the dynamic order of being, integrating time and space in such a way that the rule of fixed spatiality is surpassed in favor of a more authentic, unfrozen temporality, what Heidegger also called true time. the close kinship of time-space with depth is elaborated elsewhere. Here I only want to emphasize that once the world is brought to life by recognizing the dialectical process that underlies it, this life world is no longer mistaken as constituted by static spatiality, but is indeed understood as a time-space. Perhaps we might say then that the Kleinian life world is not a 3- or 4-dimensional space, nor a 3 plus 1-dimensional space-time, but a 1 plus 3-dimensional time-space, and nested within this life world are 3 others: the 1 plus 2-dimensional Möbius time-space, the 1 plus 1-dimensional Lemminskatory time-space, and the 1 plus 0-dimensional sub-Lemminskatory time-space. Such an account, however, would not be entirely accurate. The time and space of the life world are blended more intimately than in the classical continuum, making it problematic to view their relationship as simply additive. One plus 0 and 1 plus 1, etc. Yet in section 3.2 we did find that classical space-time originates from the more primordial spatiotemporality of the depth dimension, what Merleau-Ponty regarded as NATO space and matrix of every other existing space. So while it may not be much more accurate to describe the Kleinian life world as 1 plus 3-dimensional than as 3 plus 1-dimensional, we can and should say that 3 plus 1-dimensional space-time is projected from primordial Kleinian time-space. The other 3 space-time regimes would similarly be projected from their 3 time-space counterparts. Möbius, Lemminskatory and sub-Lemminskatory. A simple summation of projected space-time dimensions gives us a total of 10, with the lower dimensions being hidden like Russian dolls within the larger 3+1 dimensional space-time. This picture of overall 10-dimensionality with 6 dimensions concealed accords with the basic account provided by string theory. Thus we might say that our 4 temporospatial spinors spin out the 10 space-time dimensions of string theory by way of underscoring the inherent musicality of this depth dimensional string quartet. I end this section with a quote. According to Brian Greene, music has long provided the metaphors of choice for those puzzling over question of cosmic concern, from the ancient Pythagorean music of the spheres to the harmonies of nature that have guided inquiry through the ages. We have collectively sought the song of nature in the gentle wanderings of celestial bodies and the riotous fulminations of subatomic particles, with the discovery of superstring theory. Musical metaphors take on a startling reality, for the theories suggest that the microscopic landscape is suffused with tiny strings whose vibrational patterns orchestrate the evolution of the cosmos. Music of the evolving nature. String theorists have approached cosmogony by adopting the concept of symmetry breaking. According to the prevailing view, according to the prevailing view, the 4 forces of nature are conceived as vibrating strings that initially existed in a purely symmetric 10-dimensional space scaled around the Planck length. Subsequently, the perfect primordial symmetry was spontaneously broken by a dimensional bifurcation in which 4 of the original dimensions expanded to produce the visible universe we know today, with the other dimensions remaining hidden. Coupled with this was the breaking of force field symmetry to create the appearance of irreconcilable differences among the forces. However, while the foregoing account of cosmogony incorporates both dimensional and force field symmetry breaking, the two are not precisely aligned with each other in the theoretical reckoning. This reflects the fact that contemporary theorists have been unable to articulate a detailed geometric rendering of cosmic evolution. Heinz Pagels begins his discussion of the extra-dimensional Kaluza-Klein interpretation of cosmogony on an optimistic note. Remarkably, the local gauge symmetries are precisely the symmetries of the compact higher dimensional space. Because of this mathematical fact, all the gauge theories of Yang-Mills fields can be interpreted purely geometrically in terms of such compact higher dimensional spaces. And yet, for the geometric program fully to be realized, the physical events described in the standard and inflationary models of cosmic development would need to be specifically expressible as dimensional events. Unfortunately, admits Pagels, no one has yet been able to find a realistic Kaluza-Klein theory which yields the standard model. In the string theoretic application of Kaluza-Klein theory, One obvious reason for this limitation is the absence of a conceptual principle that could guide the analyst to unambiguous solutions of the 10-dimensional general equations. Solutions specifying the exact shapes of hidden dimensions that would correspond to the physical facts of the standard model. Of course, if the prevailing theory cannot tell us what the dimensional structures are that correspond to physical reality, it can hardly inform us on how these dimensions develop. In point of fact, there is really no positive feature intrinsic to the theory that provides for the evolution of dimensions. As far as I can tell, the only reason dimensional bifurcation is assumed to have taken place at all is that theorists must somehow account for the present inability to observe 6 of the 10 dimensions needed for a consistent rendering of quantum gravity. Smolin seems to put his finger on the underlying problem in calling attention to the wrong assumption physicists are all making. When they present the whole history of constant motion and change as something static and unchanging. When authentic change is thus denied, it is not surprising that no natural, parsimonious way of accounting for cosmogony is forthcoming. Conventional string theory well exemplifies this adherence to the classical intuition of changelessness in the primacy it gives to the notion of symmetry. It is in assuming an initial state of perfect symmetry that theorists must resort to the artifice of spontaneous symmetry breaking, an alleged event that, far from being the natural consequence of the purely symmetric theory, is gratuitously invoked without a compelling explanation of its basis. Phenomenological string theory affords a way out of the impasse. Here time is unfrozen. Instead of artificially appending asymmetry to a primordially perfect symmetry, a dialectic of symmetry and asymmetry is offered that permits an univocal, intrinsically meaningful account of the evolving forces of nature. This principle of syn-symmetry is implicit in the topological bisection series and its associated topo-dimensional spin matrix. For a simple illustration, consider the Möbius strip. It arises from the fusion of mirror-opposed, asymmetrically related sides of the lemniscate. We can say that through this union of opposites, the asymmetry of lemniscatory sides is rendered symmetric. However, while the Möbius can be deemed symmetric vis-à-vis the fused lemniscatory sides that constitute it, at the same time it is in self a member of an enantiomorphic pair whose own fusion produces the Klein bottle. Generally speaking, we may conclude that the members of our topodimensional family are neither simply asymmetric nor simply symmetric, but syn-symmetric. A given member combines symmetry and asymmetry in such a way that it is symmetric in relation to its lower dimensional counterpart and asymmetric in relation to its higher one. The sublemniscate is an exception to this, since it has no lower counterpart. I propose that the sin-symmetry concept, viewed dynamically in terms of enantiomorphic fusion events, constitutes a guiding principle for cosmogony. The forces and particles of nature evolve by a general process wherein asymmetric dimensional enantiomorphs fuse to create a dimensional symmetry that at once inherently gives way to a new asymmetry. To keep this article at a manageable length, I will restrict myself here with having only a topophenomenological cosmogony. Having focused our attention on the principal terms of fundamental tones of our matrices, let us now inquire into the physical significance of the overtone-undertone couplings appearing off the principal diagonals. In Table 1, these are the topodimensional enantiomorphs whose sin-symmetric fusions drive the process of dimensional generation. The overtone-undertone couplings as enantiomorphically related boson ratios. It is from their interactions that the primary gauge boson emerge, since nature's force fields evolve by a process in which the universe expands. Boson ratio fusions may be regarded as impelling said expansion. I conjecture accordingly that these primordial boson ratios interactions, which are not themselves directly observable, compromise the mysterious dark energy said to fuel the accelerated expansion of the cosmos. In phenomenological string theory, boson ratio interaction not only accounts for the generation of the four kinds of gauge boson, but for the production of the 12 fermions of the standard model as well. The 6 pairs of ratio involved in distilling the bosons also interact to yield the 6 pairs of fermions. geometrically speaking, the fermions function as dimensional bounding elements, local features of global bosonic dimensionality with local and global aspects intimately interwoven. Needless to say, this requires clarification, but I do not have the space to elaborate further on it here. I will only suggest that the purely geometrical account of boson-fermion interrelatedness I am proposing obviates the need for the unparsimonious and unsubstantiated postulation of particle superpartners given in the currently influential notion of supersymmetry. Epistemological postscript toward a new kind of clarity. In the preceding pages, I have attempted to demonstrate the advantages of grounding quantum gravity in phenomenological philosophy. Of significant benefit is the provision of a detailed and definite account of dimensional generation, one that brings string theory down to earth by aligning it unambiguously with the qualitative facts of the standard model of particle physics. Another unique feature of the new approach is its clarification of dimensions with respect to whether they are space-like or time-like. Whereas conventional string Kaluza-Klein theory is vague on this score, the phenomenological account identifies exactly 4 orders of the spatiotemporality containing a total of 6 space-like dimensions and 4 time-like ones. Most importantly, perhaps, phenomenological string theory meets Smolin's requirement of unfreezing time. However, comparing conventional and phenomenological approaches to quantum gravity has its pitfalls. It is easy to underestimate the magnitude of the change that is entailed in making the transition from one to the other. Does the phenomenological version of string theory really clarify the conventional rendition by providing more detail on dimensional patterning, as I have claimed? In general, I believe the answer is yes. But it might actually be more accurate to say that phenomenology offers a new kind of clarity, one in which the idea of detail has a rather different meaning. Assuming the conventional posture of mathematical physics, we begin from an intuition of abstract universality versus the symmetric forms that constitute the general equations. When we look to solve those equations so as to determine the particular structures that can be put into correspondence with physical reality, however, the general and particular levels of the theory are separated from each other in such a way that the sense of intuitive confidence felt about the abstract symmetries does not carry over into detailed solutions of the equations. That is why conventional string theory has had such difficulty determining which of its many possible topological solutions is the right solution. Physicists have had to play the elaborate guessing games we have discussed because their mathematical formulations afford no intuitive guidance as to the right shape of the hidden dimensions. The devil surely has been in the detail. In the contrasting phenomenological approach, the generalities intuited are inseparable from the details. since these general structures are not abstractions that must be concretized in a subsequent step, but are general things, universals that themselves are concrete. So when I say that the phenomenological version of Kaluza-Klein theory gives more detail on dimensional patterning than the conventional version, I am not speaking of details in the usual sense of particular features or instances of a pattern that itself is more general. The division of the particular and general beings tacitly assumed. Rather, I am referring to a pattern whose details are an integral part of its very submit. However, that in confronting the profound challenge of quantum gravity, the customary manner of clarification is simply not equal to the task. It is here that phenomenology can play its crucial role. And by that we ended quantum gravity and phenomenological philosophy. And we will go over to this smaller paper. It's a helping hand that somebody put up on the net, and is to accompany the YouTube clip called 5 Stages of Accepting Constructive Mathematics. The Laugh Hospital of Constructive Mathematics. In Raymond Smullyan's story, there was a planet on which the concept of humor was unknown, and laughter was treated as a disease. Those who laughed were sent to live in laugh hospitals, away from normal people. As time passed, ever more people contracted laughter, and the laugh hospitals grew into whole laugh communities, until the few remaining normal people pretended to understand humor just so that they could join the rest. What if constructive models are like laugh hospitals? What if not understanding constructivism is like not having a sense of humor? And now he's talking about the 5 stages. It's a fun talk. It's a defense of constructive mathematics, which is what mathematics becomes when you reject the law of the excluded middle. Henceforth lem, which is the claim that phi and anti-phi is a tautology. Some highlights. The rejection of them is not the same as the claim that there are some propositions that are neither true nor false. That is denying that phi 1 and negative phi is a tautology is not the same as saying that there is some proposition phi for which phi and anti-phi. This second claim can actually be proven to be false in constructive mathematics. Both the law of double negation and the axiom of choice imply lem. So to deny lem, one must also deny the law of double negation and the axiom of choice. In constructive math, proof by negation is valid, but not proof by contradiction. Proof by negation is the argument structure, suppose X, therefore not X. Proof by contradiction is the argument structure, suppose not F, therefore F. This might seem strange. Can't you just substitute each X in the first argument for an anti-X to get the second argument? The reason you can't is that the second argument involves removing a negation, while the first involves introducing one. Using proof by negation and started with anti-X, we get anti-anti-X. And of course, to constructivists, this is not equivalent to X. The lem is equivalent to the claim that all subsets of a finite set must be finite. In particular, in the Brouwer-Haitink-Kolmogorov interpretation of constructive mathematics, one cannot prove that all subsets of the set are finite. X is a classical tautology if and only if negative negative X is an intuitionist tautology. So, how do we make sense of all of this? Well, there are different ways of understanding propositions in intuitionistic logic. One simple one is to reinterpret the assertion that P as meaning P is proven rather than P is true. In this interpretation, the law of the excluded middle in this interpretation is something like every proposition is either provably true or provably false. This is the ambitious claim of Hilbert's program that we now know to be false. For instance, Gödel's sentence is a counterexample to the law of the excluded middle. We cannot prove that Gödel's sentence is true, and we cannot prove that it is false. And note that Gödel's sentence is true, just not provably so. So far as for double negation, anti-X means any proof that X entails a contradiction would itself entail a contradiction. And this is clearly not equivalent to X. Proving that proofs of anti-X inevitably lead to contradictions is not the same as proving that X in some interpretation of intuitionist logic, the interpretation of a proposition is literally tied to its current epistemic status, whether we prove it in one way or another yet. So these interpretations, P equals NP, is a counterexample to the law of the excluded middle. Let me give you an example. Assume that I am a computationing computer scientist, and I assume that this equation is impossible to clear out, to program, and then I negate that, and then thereby I've proven it is possible to count. After a time you start feeling this is absolutely wrong, although logically absolutely correct. Those mistaken contradictions or clumsy ways of making contradictions are one of the causes for making time unreal and spaces being formalizable only in a calculus. They all take leverage from a mistaken idea of it being possible to make conclusions from contradictions. It is extremely tempting, but the results are inevitably disastrous. Also a point from Edward de Bono, who show that truth is coming from negating falsehood. And it's usually in this sense we use the word truth these days, which is a shame. I say thank you very much and have a very pleasant afternoon. Bye bye for now.